Hi, this is Carter Stanfield, co-author of Fundamentals of HVACR, now in its fourth edition, published by Pearson. If you are involved in air conditioning in any way, you know that beginning in 2025, newly manufactured systems will no longer be using R410A refrigerant. Instead, they will be using lower GWP refrigerants R32 or R454B. I wondered who determines what the GWP refrigerant is, how this is determined, and why sometimes we see different numbers for the same refrigerant. I set out to answer these questions and more for myself, and now I'd like to share some of the answers I found with you. What is the science of global warming? And specifically, what science is involved in calculating global warming potential? Well, the sciences involved include physics, chemistry, climate science, and calculus. Now, before you change the channel, hold on. You don't have to really have a complete understanding of all those rather complicated subjects to understand global warming potential, or at least to have a better idea of global warming potential. Now, after this talk, you won't be able to crack out your calculator and calculate your own global warming potentials. I can't do it yet. So, since I can't do it yet, I can't tell you how to do it. But I think I can explain how all these sciences relate to global warming potential and how they come into play. First, let's review some foundational science. Radiated energy travels in waves. These waves have wavelength and frequency. The wavelength and frequency of radiated energy determines whether it's ultraviolet light, visible light, infrared light, or heat, or some other form of radiated energy. Altogether, this is referred to as the electromagnetic spectrum. Heat is a form of radiated energy that involves the molecular motion or vibration of molecules. In a nutshell, molecules vibrate when they absorb energy from the sun. Some of this energy is re-radiated as heat. The amount of energy absorbed and the amount of heat re-radiated is affected by the molecular structure. Let's talk for a minute about the greenhouse effect. The Earth's atmosphere acts as a blanket. The sun's frequencies, particularly the shorter wavelengths and higher frequencies, penetrate the atmosphere. They strike the Earth and gases in the atmosphere, and then are re-radiated as heat, but longer wavelengths. These longer wavelengths have a much more difficult time leaving the atmosphere. A greenhouse gas is a gas that contributes to this effect. The greenhouse effect is not entirely bad. As a matter of fact, Earth would not be habitable without the greenhouse effect. It's just that we need to keep it at the original manufacturer's specifications and not go altering the mix. Who determines what the GWP of a refrigerant actually is? The Intergovernmental Panel on Climate Change publishes regular reports that include the global warming potential of all known global warming gases, including refrigerants. The Intergovernmental Panel on Climate Change, or IPCC, was formed in 1988 by the United Nations Environmental Program and the World Meteorological Society. Its initial task was to review the science of climate change and offer proposals for international action. Since 1988, the IPCC has conducted 6 assessments. Each one comes up with slightly different GWP values for the same gases. So it's important when quoting GWP values for refrigerants that you identify which assessment you are using. The United States government relies on Assessment 4 for most of its regulations currently. This table shows how the 100-year GWP calculations changed among the AR4, AR5, and AR6 IPCC reports. Even though complex calculations using specific data are involved in determining the GWP of a greenhouse gas, some of the crucial data must be estimated, making GWP numbers really an estimate instead of a precise physical characteristic. So what does global warming mean? According to the IPCC, global warming is a long-term increase in the Earth's surface temperature due to human activities. These activities can include release of greenhouse gases, deforestation, and industrialization. Two terms that must be understood to understand the literature on global warming potential are radiative efficiency and radiative forcing. Radiative efficiency describes the effectiveness of a gas in terms of absorbing energy and re-radiating it to the Earth, and it's measured in watts per square meter per parts per billion. Radiative forcing measures the actual effect on the surface of the Earth, and is measured in watts per square meter. What is GWP? GWP stands for global warming potential. GWP describes how much a greenhouse gas contributes to global warming compared to carbon dioxide. In 1990, the IPCC described GWP, or global warming potential, as a ratio of the time-integrated radiative forcing of a greenhouse gas to that of a reference gas, and since then we have settled on the reference gas as carbon dioxide. Now, let's talk about the formula for determining the GWP of a refrigerant. In words, the formula is the total heat absorption of a gas times the total amount of that gas in the atmosphere over a given period of time, divided by the heat absorption of carbon dioxide times the total amount of carbon dioxide over that same period of time. In essence, it's a ratio. There are two very important factors for the refrigerant itself, and that would be its radiative efficiency and its atmospheric lifetime. Then one other factor that contributes a great deal to the number that you end up with at the end is the timeline over which the formula is going to be calculated. Now let's take a look at the formula shown here. GWP is a ratio. The numerator on the top calculates the absolute global warming potential of the gas being tested. The bottom, the denominator, calculates the absolute global warming potential of carbon dioxide, which is the reference gas. By absolute global warming potential, we mean the global warming potential not referenced to CO2. In other words, absolutely the amount of radiative forcing that gas is doing. Let's talk through the formula. The funny-looking S on the left indicates that this is an integral. It is a kind of shorthand for adding up repetitive list of terms which change with every iteration. Remember that GWP is calculated over many years. If you are calculating for 100 years, you could have 100 different calculations or more, all added together in a very long string. This would make for a messy formula. By using the funny S symbol, along with the 0 and the T, the formula indicates that the calculation repeats from time 0 until the time horizon, indicated by T. All the values from these multiple calculations are integrated or summed together as a whole, thus the name integral. T represents the time horizon, in other words, the number of years over which the GWP is being calculated. A sub I represents the radiative efficiency of the greenhouse gas for which the calculation is being performed, and C sub I is the time-dependent amount of gas in the atmosphere. Most greenhouse gases change in concentration over time. By time-dependent, we mean the amount of gas in the atmosphere at each particular iteration. dt indicates that the iterations are being done over time. So the formula is multiplying the radiative efficiency of the greenhouse gas times the concentration of the gas in the atmosphere, but it's doing it multiple times, each time with a change in the concentration of the gas due to the changes over time. All these are added together. The denominator or bottom of the ratio is exactly the same, only for CO2. Why do different IPCC assessments arrive at different GWP numbers for the same refrigerant? To start with, GWP is not a physical characteristic like density or specific heat, but instead it's a comparative number which compares the greenhouse gas potential of a particular gas or refrigerant to that of carbon dioxide. Radiative efficiency and atmospheric lifetime of different greenhouse gases can be measured in laboratory conditions. However, the atmosphere is not really a controlled laboratory condition. For this reason, we also use atmospheric modeling programs. So between laboratory measurements and atmospheric modeling programs, the data for determining the global warming potential calculations of different greenhouse gases is derived. Variations occur because the basic values used to make the calculation change over time. Since GWP values occur over an extended period of time, estimates of future concentrations of the greenhouse gas have to be made. These estimates are made using projected decay of the gas, so the period of time over which the comparison is done affects the number, and the climate model used to determine how things are going to work in the atmosphere also affects the number. So depending upon the time period and the climate model used, the GWP numbers can vary. Here is a table showing the difference in atmospheric life estimates and GWP calculations from three different IPCC reports, AR4, AR5, and AR6. Note that the estimated life varies slightly among the reports. The atmospheric life of a greenhouse gas is an estimate based on the best available science at the time of the report. These estimates are refined as more is learned about the greenhouse gases and their interaction with other gases in the atmosphere. Since GWP calculations depend heavily upon the atmospheric life of a greenhouse gas, small changes in atmospheric life estimates can produce different GWP calculations. Note the correlation between the changes in the different gas lifetimes and the changes in their GWP calculations. When the atmospheric life estimate is increased, the GWP calculation also increases. GWP calculations are done over a specific period of time, the most frequent being 100 years. But calculations of 20 years and 50 years are also pretty common. The GWP calculation for a gas with a short atmospheric life will decrease as the timeline that it's calculated over increases. Since the carbon dioxide content of the atmosphere remains relatively stable year in and year out, the radiative forcing from the carbon dioxide also remains pretty stable. By contrast, if you have a greenhouse gas that decays over time, its radiative forcing will also decay over time, meaning the radiative forcing of the greenhouse gas will get less and less, down to where it's almost zero towards the end. Since the radiative forcing is getting smaller, and while the carbon dioxide is staying the same, longer GWP calculations for gases that decay over time tend to give lower GWP calculations. For example, the atmospheric lifetime of methane is around 12 years. The 20-year GWP calculation for methane is around 80, while the 100-year calculation for methane drops to around 30. On the other hand, calculations for gases with long atmospheric lifetimes tend to increase as the timeline increases. For example, carbon tetrafluoride has an atmospheric lifetime of 50,000 years, giving it a 20-year GWP of around 7,400 and a 100-year GWP of almost 24,000. Hi, this is Carter Stanfield, co-author of Fundamentals of HVACR. I hope you enjoyed this presentation. If you did, please consider buying my book. You can find it online at Fundamentals of HVACR, 4th edition, published by Pearson, authors Carter Stanfield and David Skays.